All right, y'all, new unit. So I'm going to start with a little bit of review, and then we're going to dive into what's new. So this unit, Unit 7, is confidence intervals for means and statistic tests for means. So we're going to look at significance tests later, but we're going to start with confidence intervals. So just a little bit of review. So we're talking specifically about a mean. So what do we know about the shape? Well, the shape is going to be approximately normal. And what I'm reviewing here is what did we do when we were looking at our sampling distribution? So it was approximately normal, and this happened when n is greater than or equal to 30, so our CLT. Now remember, with means, we look at this CLT, and we say that our large counts has to be greater than 30. If you have a proportion, then use your proportion. You would use n of p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So use this if you have it. If you don't have it, we use CLT. So our center, when we're dealing with means, it's x bar equals mu. And this happens, our center happens when we have an SRS or with an experiment if we have random assignment. Okay. Our spread is our standard deviation. So our standard deviation is going to be sigma over the square root of n. Now, this is on our formula sheet. So if we look at this, this was proportions. This is what we dealt with in the last chapter, and now we're dealing with means. So sampling distributions for means. So here's our parameters for sampling distributions. And so whether we're talking about a sampling distribution or a sampling error, statistic error, which we're going to get to, we have the population standard deviation over the square root of the sample size, or the statistic sample standard deviation. So it'll be important to know which one we're using, okay? And so this is when we have our 10% condition met. So you know what this is. We've done it a million times. So 10% of whatever our overall population is, okay? Now, step back and do a little review on confidence intervals. So why do we have a confidence interval? So we have a confidence interval to estimate an unknown parameter. Now, last chapter, that was our parameter proportion. This chapter, it's going to be our mean. All right? Our confidence interval, so our formula for our confidence interval is going to be whatever our statistic is. So our sample statistic plus or minus our critical value times our standard error. Okay? So for a mean, it's going to look like this. We're going to have our statistic is going to be our sample parameter statistic, so our sample mean, plus or minus our z star times our standard deviation over our sample. And we know that z star is the critical value, so that's our percent confidence level that we're looking for. So same thing that we had before. We have our z star here and here, so I have a positive and a negative. And in between these two, right here, is where my percent confidence lies, okay? Now, this is going to be really important because we're going to move into something else where it's going to look a little bit different. But so far, it's exactly the same as when we had a proportion. All right, let's flip it over and get right into an example. So this says, a farmer wants to estimate the mean weight of all tomatoes grown on his farm. To do so, he selects a random sample of 4 tomatoes. So I'm going to just go ahead and start writing my stuff down. So I have a random sample right here of 4 tomatoes. That's my sample size. He calculated the mean weight to be 110 grams. Now that's the mean weight of his 4 tomatoes. So that is my sample parameter. This is my statistic that I care about. And that is 110 grams. Remember, with means, you have to have a unit. Okay? Let's see. It says, assuming the population of all of his tomatoes are normally distributed. All right, so I'm going to highlight this in pink because that's super important. We're going to come back to that. The standard deviation of his tomatoes in the past has been 40 grams. So this is giving us a population standard deviation. So my standard deviation here is going to be 40 grams. Use the sample mean to create a 99% confidence interval. Okay, now I know that I can go in right now and just calculate my z star. So let's do this. So if I have inverse norm and I want to know 90%, sorry, 99%. And I see that that value is 2.576. Okay, so the only other thing that I'm going to do in here is I'm going to go ahead and define my parameters. So I'm just going to say M is the mean weight of all tomatoes on the farmer's farm. All right, so let's get into our conditions. So first thing we know is at random, we have an SRS of 4, so we know we're good. We're going to check our independence now. And our independence, we have a sample size of 4, which is going to be less than or equal to 10% of all tomatoes. Now, this next one is super important. So normally, we would say is we would look at our normal, and we would say that 4 is not, so as 4 is less than 30, okay? And we would say this by CLT. However, we are not going to do that this time. And the reason for that is because it tells us up here that assuming the population of his tomatoes in his field are normally distributed. So because of that, what we're going to say is the population is normally distributed. Therefore, sampling is approximately normal. All right, so if it tells you in your story problem anything about the population being normally distributed or two populations being normally distributed, then we can assume that our sampling distribution is approximately normal, okay? All right, so let's get into here to our calculate step. So first thing that we have to state our inference method. So this is going to be a one sample Z interval for means. And remember, this Z interval means I'm using Z star. Super important. We're going to come back to that here in a minute. So my formula for that is X bar plus or minus Z star times sigma over square root of n. So if I plug this in, I get 110. That was my X bar, plus or minus my Z, which is 2.576. And then my standard deviation is 40 over the square root of 4. Okay, now I can go into my calculator and I can go into my into my stats, my tests here, and I have a one samples, where in the world is it? Did I pass it? I must have passed it. 2. Huh. It's just the interval. Let me plug this in real quick and make sure we're going to get the right number. So my standard deviation is 40, my X bar is 110, my N is 4, and my confidence level is 99. And so, yep, that's the right answer. So 58.483 to 161.52. All right, let's go back to that. So what we see here, I'm going to write this down. So this is just our Z interval on the calc. All right, so here's the best thing. You don't have to memorize anything new for your conclusion. It's the same thing. We are 99% confident that the true, now we're dealing with means, that the true mean of the farmer's, actually I'm going to say the true mean weight of the farmer's tomatoes is between 58.48 grams and 161.52 grams. And remember, you have to have the unit. Okay, so far, super easy, nothing new. Okay, so now let's go over here. So what this is saying up here on the top is when we constructed this confidence interval, we made the assumption that we knew the true population standard deviation. So we said we knew sigma. But if we knew sigma, we would actually know everything that we needed to know. So you are very rarely going to see this sigma. So what happens is when we don't know the population standard deviation, when you don't know the population standard deviation, this is how you're going to see most means. We must estimate it from the sample using the sample standard deviation S. Okay? So, however, to do this, the test statistic Z that we previously used changes. It doesn't work anymore. So now we have a new test statistic, and this is going to be a t-test. So we have this new test statistic. It's called a t-test, and this becomes our t-distribution. Oh, that's a T. T-distribution. All right, so that's what it tells you right here. The t-distribution, which is also called the student's distribution, is a family of related distributions which depend on a parameter called the degrees of freedom. So I'm going to show you what degrees of freedom is. I think it makes it a little easier to understand. It is denoted as DF. We use DF on the calculator, and you'll use DF on your free responses. It's easy to calculate. What we know is DF equals n minus 1, and n is your sample size. Okay, so t-distributions are unimodal, symmetric, and bell-shaped. So they look like the normal distribution, but t-distributions with a few degrees of freedom have longer tails and larger standard deviation than the normal. So let me show you on this diagram, because I think for me this made a lot of sense. So what happens is I'm going to highlight this curve here first. That is our standard normal curve. And so what happens is we have our mean here at 0, and then we have 1, 2, and 3 standard deviations, and 1, 2, and 3 standard deviations in the negative. And what happens is we know that this accounts for 99.7% of all the data. And so what happens is our line down here at the base of this curve is super, super low, because we know that we've accounted for almost all of the data underneath this curve. Well, now what happens when we talk about a t-distribution is this area that we have here, they say it's fatter, but it's just not approaching 0 until we get clear out here wider. So if I look at, let's do this one first. So if I look at this t-distribution right here, it's going to bring me to this point. So what you see is I have this extra area that's accounted for that's right here. Now what this is this is a t-distribution with a degree of freedom of 20. That means my sample size was really 21, because my formula is less than 1. Okay, so now let's look at this one. So I have this green curve right here. Eesh, sorry about that. Here's my green curve. And what happens is now you see that as I come out here, this data under the curve is even higher. I have more data that is out here. So it's not, we have this area, okay, hold on, let me step back. This is a degree of freedom of 4, so this means my sample size is 5. So what happens is, as we have these they look like normally distributed curve, we have these tails that come out here. And the tails with a smaller sample size are fatter. They are wider. So we have, it's going to be closer to a normal distribution as n increases. So because of this, we have more variability when we have a smaller sample size. We already know we have more variability with a smaller sample size, but this is what it looks like. So this just says the larger our sample size gets, the larger degrees of freedom we get, the closer the t-distribution will move towards the normal standard distribution. We see that. The red line is closer to the yellow line than the green line. Okay, now here's what happens. So we're going to calculate our t-distribution, and we're going to use inverse t. So what happened before is we would have a confidence interval, and we would say that within this confidence interval we have some percent C. Now what happens with t is we have this t star now, and we have the same thing, a plus or a minus t star. But now what we're looking for, our degrees of freedom as n minus 1, is really defining what is happening here. It's defining what's happening in the tail. So this is our tail proportion, and the tail proportion is what we're calculating. So the area listed has to be the tail probability of the interval that you're finding. So when we did proportions, we would find the area that was between our z-scores. Now we're finding the area that's in the tail of our distribution. Okay? So let's practice that so you see what that looks like. So find t star for the following situations. So I have n of 5. That means degrees of freedom is n minus 1. So my degrees of freedom here is going to be 4. And if I have a 90% confidence interval, so I don't know, I'm just going to say this is 90% right here, then that means that the other 10% is going to be in the tail, right? So this is going to be 0.05%, and this is going to be 0.05%. All right? So this is the value that we're going to plug into our calculator. So if I go to inverse vars, I go to distribution, I would go down here to inverse t. And it's going to ask me the area. So my area is going to be 0.05, and my degrees of freedom is going to be 4. And what I get is I get an area of 2.132. That means this value is negative 2.132, and this value here is 2.132. So what did I plug in? I plugged in the area, not this 90%. I plugged in the tail. So when you think about t-distribution, think tail. Okay? So now let's look at our confidence interval with a sample of 25. This means my degrees of freedom is going to be 24. All right? So this doesn't change. This is still 90, which makes this part still 0.05. So when I plug this in now, I'm going to say my degrees of freedom is going to be 24, and I get a t star of negative 1.71 and 1.71. Okay. Now, the other thing to think about is if you think about this truly in terms of standard deviation, so when we look at our confidence intervals of 90 and 90, we see that with a small sample size, we are further away. I know I drew these about the same, but 2.3 is going to be further away. It's actually going to be out here, right? And 1.71 is closer. So we said that a minute ago, that as our sample size increases, then our that's going to impact the width of our interval here, which is going to affect the area that's underneath that tail. All right, so now let's practice this. Let's see what this looks like. So when we are calculating a confidence interval for a mean with an unknown standard deviation, so this is the one that you really have to make sure you know. We're going to use t star as the critical value for the t distribution. So what happens is our formula here becomes x bar plus or minus t star s over the square root of n. Now, if you compare that to what we had a minute ago, let me grab it. we said that this is our population standard deviation and Z. The only thing that's changed is now we're using T and we're using our sample standard deviation. All right, so this is called, we just talked about this is a one sample T interval for a mean. All right, so how does this affect our conditions? So no change, SRS or random assignment. Okay, independent. When sampling, check this 10% condition. This has not changed either. Okay, so for normal, if I don't have a proportion, I'm going to check CLT. This is my large counts. Okay, it will tell us that this is approximately normal. Now, if N is less than 30, now our tomato example a minute ago, N was not close to 30, but it told us it was that the population proportion was normal. If N is less than 30, then we have to have the original population be approximately normal. This is what happened in the last problem. If it is not approximately normal, so if this condition's not met and this condition's not met, then we have to do this. Graph the sample data to make sure there are no outliers or strong skewness. Now, we can do this with a histogram, and we can do this with a dot plot. Either one of those would work. Now, because they changed the free response criteria this year, they said that there's no graphing. I'm going to assume that the graph will be supplied, but I'm going to show you the fast way to do this just in case it's not supplied. It's supposed to be, but just in case, I want to show you a fast way to do this. Okay? All right, let's go to our example. All right, so it says, you recently read an article that said averaging 300 minutes of exercise a week will help you fend off cancer. A random sample of 10 U.S. adults was taken, and they were asked how many minutes of exercise they get each week, and the data is given below. So it's right here. Construct a 95% confidence interval to estimate the true population mean. Based on the confidence interval, do you believe adults are exercising enough to ward off cancer? Okay, so here we go. Let's go ahead and talk about what we know. So our communicate part. I'm going to say that mu is the average minutes and adult exercises per week. All right, so I've got all this data that's in here. I need to get my statistics. I'm going to put that right into my calculator. So what we're going to do is we're going to go in and we're going to do one var stats. So if I go in and do edit, I'm going to list my list. I'm going to have to put these numbers in, so I'm just going to go up here and clear this list out. And I'm going to say 265, 274, 281. Okay, so there's my data. It's in L1. So now I'm going to run stat, calc, and one var stats. So I have one variable right here. Here's what I get. So let me write down all of my information, everything that I know. So now I have my X bar, which is 283.2. I have my S sub X, which is 22.039. I have my N, which is 10. I have 10 samples up here. And I really think that's all I need. I think that's all I need. Okay, so the other thing that I know is that I need a 95% confidence interval. All right, so because I was not given my standard deviation, that's why I need S of X. And if I have this, then that means I'm going to have to find my T value, so my T star value. So what I know is if this is, and you don't have to do this, but I'm going to do this right now. If this is a 95% confidence interval, that means I have 5% left. That means it's going to be 0.025 on this end and 0.025 on this end. Super important. This is what I care about. I care about what's happening in the tail. Remember T star. So if I plug this in, so inverse T, my area is now 0.025. My degrees of freedom, so let me make sure that you have this listed somewhere. Your degrees of freedom are going to be 9. It's 10 minus 1. So this gives me my T star value as 2.262. 2.262 is my T star. Okay. I think that's all I need. So let me go in here and do conditions. So with my conditions, the first thing, is it an SR? Is this an SRS? And it says here a random sample of 10 adults. So yes, we know that that is true. So now I'm going to check my independence. My independence says 10 is less than or equal to 10% of all adults. And that's for sure true, right? So now I'm going to look at my normal. So normal, I would say n is less than 30, and this is not true. So because this is not true, I have to have a graph. So I already put all of my data in my calculator. So all of my data is right here in L1. All right. So what I'm going to do is I'm going to go in here and I'm going to turn my stat plot on. So I'm going to go second y equals, and I have this plot. I'm going to go over here and turn it on. And then if you go down here, one of your options is a histogram. So I can do this histogram. My data's in L1. And so I can go ahead and, oops, I didn't want to do that. I can go ahead, I've got all of this data, and then I'm going to go ahead and do zoom stat, so zoom 9, and here's my histogram. So if you look at this, you'll be like, uh-oh, I've got this outlier that's over here. But I'm going to change my window a little bit to see if this is really true. So if I do this, let's just do... let me change my window. I'm going to make these numbers kind of match my numbers that I have up here. So if I start at, it looks like my min is 243. So if I start at 240 and I have a max at, let's just say my max is 340. And this time I'm going to make my scale 20. And I graph this again. Uh-oh. Hold on. Let me see what I did wrong. Oh, it should be 340. And I graph this again. Now, my histogram doesn't look like it has outliers. It looks like it's a little bit skewed, but not really. So what I'm going to do is I'm just very quickly, since I don't have one right here, I'm going to graph this. And the thing is, if you hit trace, trace is going to give you the values. So right now, I know I have one of these. So I have this count of 1, and this bar is going to be from 240 to 260. If I go over one more time, I have 3, and this is going to be from 260 to 280, and then I'm going to have 4, and that's 280 to 300. So hopefully you see where I'm getting these numbers. And then I'm going to go over here, and I'm going to have a value of 1 again and a value of 1 again, and this goes to 320 and then 340. So if this is provided, all you have to say here is that the data shows no potential outliers or strong skewness. Okay, and just kind of as a reminder, how I got this, I went to stat plot and I turned this on, and then I did stat zoom, which is option number 9 when you get to zoom. So zoom stat, which is number 9. And then I played with my window just a little bit to make it look like it was it didn't have that one outlier that was out there. Okay? All right, so this requires a little bit more work. Hopefully this will be provided, and all you have to do is say that the data shows no potential outliers or strong skewness. All right, so let's get in here to our calc. So my calc is a one sample T interval for means. So again, super important. I've got to have this guy right here. All right, so my formula is going to be my x bar plus or minus T star S over the square root of n. And I have all this data. I got all this data from my one bar stat. So I know this is 283.2 plus or minus 2.262 times my S value, which is 22.039, over the square root of 10. Okay, now I'm not going to even plug that in. I'm going to go to my calculator, stat, calc, and then one sample, two sample, t-test. I'm going to use this one. Oh, look how great this is. I just love this because I put everything in one bars. Everything's already there. Oh, wait, hold on. This is a t-test. That's not going to work. Sorry, don't listen to me. That's not right. Hold on. I need a t interval. One sample t interval, not a test. And, okay, there's all my data, including my 99, but it's not 99. I need to change this, 95. All right, so what does this give me? This gives me 267.43 to 298.97. All right, so that's my confidence interval. So now let's do our conclude real quick, and then we're going to be done with this. So my conclude says we are 95. Hold on. I think I might have just run that wrong. Oh, no, I did 95. We're good. We are 95% confident that the true average, or you can say mean, the true average, the true mean of time adults exercise per week is between 267.4 minutes and 298.97 minutes. Now, let's look at what the question's asking. Do you believe that adults are exercising enough to ward off cancer? So what I'm going to say, it says, do you believe? I'm going to say because the interval does not contain 300 minutes. I do not believe adults are I don't know how to spell that, exercising enough to ward off cancer. All right, boom, we're done.